All right, how's it going, everybody? We are here on Thursday, February 11th, and today we're starting chapter 2. We wrapped up chapter 1 last week. Last week we did 1.8 and 1.9, which was our linear systems, and then some substitutions that we saw. This week we're finally introducing systems of differential equations. So we're going to look at, just like you've seen systems of equations, where we have two different equations with two different variables. We're going to discuss systems of differential equations for quite a while now. And in fact, we're going to be discussing systems for almost pretty much the entire rest of the semester here. So really chapter 1 is sort of getting our basis as to like how to think about differential equations, sort of for the purpose of us actually being able to discuss systems for most all of our meaningful conversation. One of the other things that we're going to see today is that even differential equations that are not necessarily described as systems can sometimes be converted into systems, and that's actually going to make it easier for us to perform the analysis once we get comfortable with our system stuff. So kind of the way that this is going to work as our like layout here is that chapter 2 is going to be sort of like our conceptual introduction to systems, and chapter 3 is going to be like our mechanical look at systems. It's like, how do we actually like solve these differential equations? How do we actually classify all the equilibria that are associated with them? So chapter 2 is sort of our system concepts, and chapter 3 is sort of like our system techniques. And then we're going to see in chapters 4, 5, and 6, those are going to be sort of our like more advanced techniques to handle more complicated situations. So let's do what we always do, and let's start with things we have already seen. So far, we've kind of spent most of our time kind of following along this same path of talking about these population models, right? We started our very first differential equation we see right here. Then we said, okay, maybe we should upgrade this to talk about a carrying capacity. And then we said, okay, it's also the case that like if a population is size 1, it shouldn't grow. And even if it was size like 50, it still probably shouldn't be growing if this is like a population in the wild with no human intervention. And that caused us to introduce a maximum viable population term as well. So these three populations describe exactly what I said. The exponential nature of unchecked growth, the limitations associated with resources in the environment, that's our carrying capacity, the minimum necessary population for sufficient mating interactions. And again, it's not just that we need two for a species to survive, it's like there needs to be like many, because if we're talking about animals in the wild, they still need to like a male and a female need to still encounter each other if they're going to reproduce and stuff. And so there needs to be enough that there's going to be random encounters that they're going to have so they can mate and produce offspring, stuff like that. Right? So, if we're following along with the chain of thought that we've had in the past, which is, well, can we upgrade this to be more representative of how populations actually grow? We went from this one to this one to this one, and what we feel like we're doing is we're like honing in on like an actual, reasonable, true description of how populations grow. But what's sort of obvious here, hopefully obvious to you, is that pretty much every single biological population, I never want to say every single, I think that's too much of an absolute statement right there, but pretty much every single population on Earth, the size of its population is in part controlled by other populations of other species that it interacts with, right? So when I say what affects the size of what else affects the size of a population of a species, I'll say interactions with other species. So I think if we're to make our next improvement to our population models, the next thing to start doing is to describe other populations and how they relate to the population of interest. All right, so as we introduce our systems discussion here, it's really still following our same thread that we've been on for the entire course so far, which is, can we improve our population model better? And I think the answer is yes, by also including content associated with the other populations with which that population interacts. So the very, and I'll say it for sure, it's a cliche example here, rabbits and foxes. Although in general, foxes, for the most part, do not hunt rabbits, so this is actually like a terrible example right here. But a very common example to think about a predator-prey relationship would be rabbits and foxes. So what we're going to do, our first system of differential equations here, is going to be an equation representing, not just using P for population, but representing R for the rabbit population, and using F for our fox population. And notice that's a capital F for the fox population right there. not lowercase f, which is describing the function associated apparently with the rabbits over there. And notice that since r and f, and this is kind of important for a second right here, small important thing, since these are populations, it should be that r is certainly greater than or equal to 0, and that f is greater than or equal to 0. We're not talking obviously about negative populations. We will talk about scenarios coming up where we obviously can have negatives in these guys right here. We'll see easy to understand scenarios for that. But for this particular population example, we only have positive populations, or 0. So what we might wonder here is, what are these expressions going to look like? What are these differential equations, or what are they going to look like? What kind of structure are they going to have? We see some ideas that we have up here, and let's think about how these ideas are going to relate to the fact that these are actually describing interactions between species. Right? So what we should do is we should do the same thing that we always do in math, which is think about the easiest stuff first. And when I say easy stuff in math, what I mean is, how do you jam the number 0 into this and make sense of it? So, given that f of rf is the rate of change of rabbit population over time, what can we say about f of r0? So this is asking, in more just direct English words here, is saying, if there are no foxes, what will happen to the size of the rabbit population? So that 0 is in the fox population slot. So I will say here, if there are no foxes, rabbit population will increase. No predators means the prey population is going to be able to just grow because it doesn't have anything preying on it. Now, on the other hand, over here, our partner statement, since we're talking about a system of two equations, we're going to have kind of two questions that we're always going to ask every time. Given that g of rf is the rate of change of fox population over time, what can we say about g of 0f? So this is saying, if there are no rabbits, what will happen over time to the population of foxes? And again, we're considering here that this is in a sense like a closed system. This is certainly an artificial example, kind of like all of our examples are. It's just a model. But in my mind, I'm sort of thinking to myself, foxes live by eating rabbits. And obviously, foxes eat lots of things, not just one thing out there. But here we're thinking, if this is a closed system that exists, that contains only foxes and rabbits, if there were 0 rabbits, we would expect that fox population to heavily decline because they don't have anything to eat, right? So if there are no rabbits, fox population will decrease. Right. And so I kind of think that we should kind of make some other, maybe kind of verbalize our statements here a little bit differently here. That should be saying to me that f of r0 should be greater than or equal to, or should be strictly greater than 0. That says my rate of change of rabbit population is positive. Oh, I can't write maybe with 2 y's. Maybe, and I'm just giving an example right here, and to say things like f of r0 will be equal to 2r, right? Some positive number right there. I'm artificially sort of just sticking a 2 on there, just for example, right? Similarly down here, we can say g of 0f. We know it should be negative. If there are no rabbits, the rate of change of fox population will be negative. And so here we can maybe just say, that we get g of 0f is negative f. It's going to be decreasing proportional to the number of foxes that there are, or something like that. So these above statements now describe kind of not what we're actually interested in, right? What we're interested in is what happens when they interact. And these 2 statements that we just made are exactly what happens when they specifically don't interact. What happens when there's only one of one species and none of the other, right? Or not only one. Only one of the species has a positive population, the other species has a 0 population. So what we really want to ask ourselves is, What happens when rabbits and foxes interact with each other? How does that alter the population counts for them? So what happens to the size of the rabbit population when rabbits and foxes interact? Well, the rabbit population should decline when they interact because rabbits and foxes don't play together, as my child's books will suggest. Foxes eat rabbits, so this is a negative experience for the rabbits, but this should be a positive experience for the foxes, right? So rabbit population declines with interaction with foxes. And we can say that fox populations grow when they interact. Interact, that's such a nice euphemism for hunting, interaction. The rabbits and foxes are just interacting with each other. All right. So what that seems to me then is that we can combine these pieces of information to build a predator-prey model, right? What we want to imagine for ourselves is that there should be some term that represents an interaction term. We've come up with some terms that represent the standalone terms. Notice that this 2r term didn't include f in it, because if it did, then it would have f being 0, and then this would be 0. We want it to be a positive number, so it couldn't possibly contain any foxes. So this is saying, when left alone, this is the rate of growth of rabbits. When left alone, this is the rate of decline of foxes right here. Right? What we want is an interaction term. So how should we build an interaction term? Well, here's the thing I'm thinking. If there's like 10 rabbits and 1,000 foxes, there's going to be very few rabbit and fox interactions. Similarly, if there's 1,000 rabbits and only 10 foxes, there are very few rabbit and fox interactions. On the other hand, if there's 100 rabbits and 100 foxes, there's going to be lots and lots of rabbit and fox interactions. So what I'm kind of feeling out here is it seems like a very simple thing that we could do is just multiply together the rabbit population and the fox population and take some proportion of that to describe, proportional to the product of the rabbit and fox populations should be a measure of how much interaction they have and what does that do to alter their populations. We know that this interaction term is negative, this interaction term is positive. So we can put these two ideas together, what happens when there's no interaction, as well as what happens when there is interaction, for our first sort of sample predator-prey model right here. And so here we can see exactly the things that we had described. First, ignore the two terms on the back right here. Completely ignore these two guys right here. The rate of change of rabbit population is positive if there's only rabbits. The rate of change, I'm glad I'm verbalizing this, the rate of change of fox population is negative if there's only foxes. However, when the rabbits and foxes interact, that is going to be a negative experience. It's going to cause a decline in the population size for rabbits. And when the rabbits and foxes interact, that's going to cause growth for the rabbits and foxes. Now, this 0.9, this 1.2, these are conveying several things. One, this is part of a proportionality constant that is saying how, like in a sense, how much does this impact our population? And you should recognize things like a single fox eating like a single mouse is not going to necessarily grow the fox population, right? But maybe if these foxes are scavengers and like an elephant collapses and dies, that might feed hundreds of foxes over like an entire generation, right? So this constant coefficient that's sitting up front is helping us measure the sense to which how much does one interaction change the population over time. And so we should think things like if the thing that you're preying on is something very, very small, then that should be a small coefficient. If the thing that you're preying on is huge, it should probably be a much larger coefficient. So again, picture if this is like mosquitoes trying to hunt elephants, then all it takes is one elephant, and we're going to have like literally millions of mosquitoes could probably be introduced into the population due to one elephant's contribution of resources right there. So so these are in a sense a little bit arbitrarily selected for our purposes right now, but they are kind of like helping to give us that sense of like how helpful was it or how hurtful was it to your population to have that interaction, which in this case, by the way, basically means a hunting episode right here, because we're talking about a predator-prey model. But what I want to suggest to you is that predator-prey is certainly not the only type of relationship that two different species can have. So I think a good thing for us to stop and think to ourselves here is consider two generic populations, X and Y. My question to you is, rather than a predator-prey relationship, how would you describe each of these relationships here, using some biology vocabulary words that I think that we all probably kind of like know a little bit about. So stop for a minute and stare at this. If you're watching this after the fact on the YouTube video here, you should pause this and you should ask yourself, what do the positives and negatives inform me about the nature of the relationship between the X population and the Y population? So what I'm seeing in the first example is this. In the first example, what I'm seeing is, if the X animals are all left alone, they'll grow. And if the Y animals are left alone, they'll also grow. It looks like they both are going to grow if separate from each other. But what I'm also seeing is they're going to grow even faster. The X populations are going to grow even faster when they interact with Y. And the Y population is going to grow even faster when they're interacting with X right there. It looks like this is a cooperative relationship between these two species, right? Or maybe symbiotic might be a good word right here, because the interaction is beneficial to both species, right? Both species benefited, grew from interacting with one another. Now, on the other hand here, what happens when we introduce these two negatives right here? Well, it looks to me like in this case, the X population, if there was none of the Y, the X population would decline. And the Y population, if there was no X, would also decline. But it looks like they will have a positive contribution to the population size for both of them if they interact. So it seems like in this case right here, X and Y are both dependent on the existence of the other, and if either of them was removed, then they wouldn't be able to survive without them. They would only have a negative rate of change of population. So this is dependence right here, right? Without the other population, it couldn't live, and that's true for both species that we're seeing right there. All right. Now in our final example right here for X and Y, it looks like in this case, if X is left alone, if there's only X stuff, it's going to grow. And Y, if it was left alone, if there was only Y population, then it would grow. It looks like each of them experience negative interactions by having other members of the opposite species being around. But if they're left alone, they're going to do just fine. This, to me, looks like competition. Right? So this might be like deer and elk. They use the same resources. I'm not a biologist. I don't know if deer and elk really negatively affect each other's populations, but I'm kind of imagining they consume the same resources, right? They both graze in the same grasses and stuff like that. If there was a huge number of elk, it might, use up too much of the space, eat all the good grass, so that there can't be any of that for the deer, and vice versa. One of them would be happy to survive on their own, which is why we get the positive solo terms right here. But when there's too much of one, too much of the other, then they have that competitive interaction right there, where they both experience negative population growth by having interactions with one another right there. It's definitely the case. I'm thinking to myself right now, like invasive species for fish and rivers. I do know that that's the case. For example, in Yellowstone National Park, there is not one single fish in all of Yellowstone that is native to Yellowstone, because we introduced, I think that they were just, all my fisherman friends are gonna get mad at me. I think it was that there was like golden trout and rainbow trout, and then we wanted to fish more enjoyably, so introduced like brown trout. Whatever it is, the fish that we introduced is much larger than the others and outcompeted the others to the point where the other population declined to zero, and now there is only members of the invasive species of trout that are in all of Yellowstone. So it's one of these places that we sort of think is like a wildlife like preserve, like one of those places that and when you go to places like Yellowstone National Park, man, it feels like you just went back in time like 50,000 years, and it turns out like all that park is a gigantic lesson as to how much humans have screwed up environments and stuff like that. There's a ton of stories like that associated with Yellowstone. So in any event, competition here, we're on your own, you do fine. Interactions with the other species are negative for both species. They're competing over the same resources right there. So lots of different things can happen. Predator-prey, symbiosis, dependence, competition. I would have to guess there's probably some other types of relationships that biologists could inform us about out there. I think that was at least good for us to think about our positives and negatives in the system and how these things relate to one another here at least. So let's come back to our rabbit and fox population. We're going to talk about this guy here for a while. So let's talk about equilibria here. When we talked about our one-dimensional systems, we found equilibria, y values, wherever dy dt was equal to 0. This said y is not changing. That's literally the definition of an equilibrium. You reach a state of rest, right, where nothing changes anymore. Well, if we want to have no change, then it just needs to be that both of our populations aren't changing over time, right? So dx dt and dy dt both need to be 0 at the same, for like collectively, for there to be no change whatsoever in population. And by the way, I do want to point out to you just briefly right now, we are going to talk as well about what's the deal with just when one of the differential equations is equal to 0, but not the other. That will be a thing of consideration for us that we're going to kind of like study a little bit later. That's just us getting a little bit ahead of ourselves. We don't want to introduce 90 new things today. So we'll talk about that later. A true equilibria in a system is happening where every single differential equation is equal to 0. Straight up no motion. I don't care how many variables we're describing, none of them are changing, right? So let's go ahead and find the equilibria for this system, and you should immediately recognize that that means that you do need to remember how to do algebra here. So doing a little bit of the algebra right here, I'm going to set this guy equal to 0 and set this guy equal to 0 here. And the thing that I'm seeing, and like taking this first equation right here, is that there's an r in both terms, but not an f, so maybe I'll factor that guy out. And so I'm seeing that this first equation is equal to 0 either when r is equal to 0 or when f is equal to, and what do we get right here if I set that guy equal to 0 and divide 2 divided by 1.2? And that's like 20 over 12, that's like 10 over 6, it's like 5 over 3. Right? So r equals 0 is one way that I can have my first differential equation be equal to 0. The other way is I can have f be equal to 5/3. If f is 5/3, then what we're going to get is 2r minus 2r equals 0. So if f is 5/3, I don't care what r is, dr dt is 0. If r is 0, I don't care what f is, dr dt is equal to 0. So I have not found any equilibria yet, because I still need to ensure that the oh my gosh, did the same thing again, I obviously copied and pasted that one before. Now I need to do the df dt equation, the Fox equation, and also set that guy equal to 0 right here. So now I know that these are two r and f values that will cause the first equation to be 0. I want them to also be associated with the second equation being equal to 0. So now my next move right here is to take this equation here and do both of these things with it. So now I'm going to say for the Fox equation, I'm going to say df dt equals 0 and r equals 0. That's my first case right here. That's going to say 0 equals negative f plus 0. Well, that just says f is equal to 0 also, and so this concludes to me that a r comma f of 0 comma 0 clearly seems to be one equilibria location. R equals 0 makes dr dt 0. I made df dt equal to 0. There's the 0 right there. I'll slide over so I'm not falling off my edge right here. It does look like I'm going to need a little bit more room right here. But in any event, I have used the idea that r equals 0 as one way to make it happen. Another way to make it happen would be to make f be equal to 5/3. So I'm going to do df dt equals 0 and f equals 5/3. That's my new set of conditions here. In this case, df dt equals 0. There's the 0 equals. F is going to be 5/3. So I'm getting negative 5/3 plus, what is that, 9/10? I'm going to write, since I'm doing fractions here, I'll write 0.9 is 9/10. And that's going to be times r. And f, again, is 5/3 right there. So it looks like I'm going to want this to be in terms of 30ths. So I'm going to add 5/3 over, but make it 50 30ths equals, it looks like this is 45 30ths times r. So dividing this, I'm going to get 50 over 45, 10 ninths. So it seems to me like we're also getting, so there's one equilibrium right there, and it seems like we also found that our F equals 10/9 5/3 is another. So I did the algebra required to identify what RF ordered pairs will result in both drdt and dfdt both being equal to 0, meaning the rabbit population is not changing and the fox population isn't changing. The first one, super easy to interpret. Obviously, if there's no rabbits and no foxes, then the rabbit population isn't changing, the fox population isn't changing. That's sort of our trivial equilibrium. Or one that's actually interesting is kind of helping us see what sort of relationship we might have where they're both in balance with one another. Where there's enough rabbits that the population of rabbits will be maintained. The foxes are going to eat some rabbits, but it seems like the foxes that are eating rabbits are eating the rabbits at exactly the rate at which the rabbits are increasing their own population by mating. And so they're in a nice equilibrium balance here. That's our pre-humans balance right there, back when nature actually used to exist in equilibrium anywhere before we got involved, right? So what I kind of want to do now is say to myself, what we did with equilibrium in the past is we kind of used those to help us describe sort of like a graph that helps us visually see the solutions of interest to us, right? So here's a nice thing to see, and I'm kind of trying to keep our equations on screen as I scroll down here. By the way, PP, predator-prey. Notice that our predator-prey model is autonomous, right? We have no, what are you doing here, Word? Stop doing, I'm not clicking stuff. Holy cow. It's autonomous, right? I don't see any t's in here. That is a derivative with respect to time. It is describing how the rabbit population changes over time. But the point is here, if there is 100 foxes and 50 rabbits, the changes that I expect for them both to experience from that initial condition are the same today as if we were in those conditions a month from now. Right? Now, it's technically probably the case that seasons would actually impact that. So if we're trying to do an excellent, perfect job of modeling this, there probably would be some time terms in there that says, rabbits are going to grow much more in the spring and summer, and they're probably going to grow less in the winter and the fall, stuff like that. But we're sort of assuming that we're in an environment where they have equal ability to mate in all seasons, stuff like that. So we're not bringing that into the conversation. We're keeping this simple enough to be able to do the analysis for day one, obviously, of systems. So the important thing is this: since it's autonomous and it has no dependence on time, what we knew from our one-dimensional systems in chapter 1 is that there being no dependence on t means we don't need a whole slope field. We can just collapse that down onto one vertical line, one phase line, because there was no dependence on some other variable t. So we didn't need 2 dimensions. We only needed 1 dimension because one of the variables sort of wasn't present. The t wasn't present. So in a sense, we're going to get 2 phase lines. One phase line associated with drdt, one phase line associated with dfdt. So it's sort of like us taking now the one-dimensional graph that we got from drdt, its phase line, a one-dimensional graph from dfdt, its phase line, and what is that going to make? Well, now it's going to make a 2D picture, but the 2D picture is in a sense going to be a combination, a perpendicular combination of their 2 phase lines, right? So this is referred to as a phase portrait or phase plane. And fortunately for us, our technology is going to graph these things for us, right? Just like we've been graphing these things at that website, it's going to do systems of equations for us as well. And so let's go ask it to do that for us now. One of the things we certainly want to confirm is, are we actually experiencing the equilibrium at 0 and at 10/9 5/3 like we are anticipating? Like, are we going to be able to see this in the picture? Now, before I go do that, I want to point out a couple of really important things here. One very important thing: the default settings are going to be super misleading for the actual behavior of this. And I'm going to show you the bad settings, and then I'm going to show you the good settings here. So we're going to want to make sure that our step size is very small. This makes it do more calculations, but that and that h is exactly like our h in Calc 1, right? This is like, or like saying like a Riemann sum. Rather than having our rectangles in our Riemann sum be this wide and there being 10 of them, it's much better for them to be 1/10 as wide and there to be 100 of them. You have 10 times more computation to do, but your estimate's going to be much, much closer to the actual approximation of the area underneath the curve. So you should think about it that as like your delta x in a Riemann sum. The smaller we make it, the better our approximation gets to the true behavior, and that's why making that h value smaller is going to be better. It starts at the h value of 0.1 because it doesn't want to put itself in a situation where it might have to do a mountain of calculations right off the bat. So it's giving you a very modest h value, just out of potential concern for, it doesn't want to have to take 20 minutes to compute one curve if you make the h 0.00000001, right? But we'll have to fix that or we're going to get some misleading things. The other thing that I'm noticing out here is that its default is to do sort of one of the lamest techniques for computing these lines right here. We want to upgrade it to a slightly smarter technique, and I'll just say it like in one sentence right now. The default is the Euler technique, Euler's method, and Euler's method is a linear approximating thing. The Runge-Kutta-4 method is going to be a quadratic approximating thing. So instead of using lines to make the approximations, it's going to use quadratics. It's just going to get a little bit better of an approximation because it's using second order polynomials instead of first order polynomials to approximate the curve. So also altering which technique is used will also increase the accuracy of the graph that we're generating. So that's thing one, is we need to be able to alter these sort of settings in here to get more accurate pictures. The other thing that's really important is that there is going to be a new section of the website that we're going to look at that's at the bottom of the page, numerical solution tables and time plots for systems. That's going to help show us other graphs that are going to be of interest to us in these rabbit and fox populations. So I'm just saying there's more than one graph that we're interested at at the website over here. So let's go ahead over there and take a look and see what we see here. So my intention is to go over there and to throw in exactly this equation. I'm going to use x for rabbits, y for foxes over there. So popping on over. Bluffton.edu. Thanks to the dude at Bluffton that made this, Daryl Nestor. He's our man this semester. We can see right here, we get system right here. So this is going to give us two equations, dy dt and dx dt. So our first equation here in terms of x was 2 times x minus 1.2 times x times y. Our second equation down here was negative y plus 0.9 times x times y. So that's exactly the differential equation that we were originally given. I guess I can zoom in at least a little bit right here. Oh, okay, don't do that. Here we go. So let's go ahead and hit the thing here. I'm going to hit enter. And so it's now plotted the phase plane. Immediately, my first thought is this. Why the heck are we centered on this plot right here? I want to talk about positive rabbit populations, positive fox populations. I only care about the first quadrant of this thing. So let's go from just 0 to 3 and 0 to 3 right here. The reason I know that 3 is an acceptable upper bound on this for my consideration is because I know, real quick, flipping back over here, I know that my equilibrium of interest that I'm sort of trying to like double check with my graph, this location, this x and this y are both decimals between 1 and 2. So since I'm trying to like kind of verify my work at 0, 0 and at like 1.1 and like 1.6, I think that 3 is good enough for x and y coordinates. So coming back over here, here is the phase plane that I'm seeing. Right now, I'm going to do the bad version of graphing first, and here's the important thing to see. We have a relatively large step size, and again, you should be thinking of this as like a Riemann sum. This is saying your rectangles are 0.1 wide, and there's 10 of them. What you know is that we would get a better approximation if they were 0.01 wide, a tenth as wide, but 10 times as many rectangles. We're going to improve our approximations. Very, very similar calculus concept is happening here. So I'm going to leave it like this, and we're going to see, click once, and what I'm seeing here is, ooh, interesting. So what this is showing me is this. Starting at this location here, and knowing that our x equation is our rabbits and our y equation is our foxes, it seems like what happens from here is the rabbit population grows. Not much change in the fox population. But the fox population is growing now too, because what happens as the rabbit population gets bigger is there's now more rabbits for the foxes to eat. So the foxes start eating them, so now we're getting some vertical growth. Now the fox population is also growing. But what happens when the fox population grows enough? Well, now there's more foxes, and now they're eating more of the rabbits. So now we're heading back to the left as we go up. The up is the fox population growing. The heading to the left is saying now they're eating more rabbits than rabbits are mating and producing. But eventually what's going to happen is the foxes are going to have eaten so many rabbits, now we're at the top of this curve right here, that now we're kind of thinking to ourselves that now there's so many foxes relative to rabbits that now there's not enough rabbits for the foxes to eat. So what's going to happen? Well, the fox population is going to decline. And once the fox population has declined enough, it's now going to make it possible for the rabbit population to begin growing again. That kind of makes sense, the cyclical nature of that, the balance there. Lots of rabbits leads to more foxes. More foxes leads to less rabbits. Less rabbits leads to less foxes. Less foxes leads to more rabbits, and the cycle continues. The strange thing about this graph is it seems like this is just, in a sense, like spiraling out of control here to where eventually we're just getting massive population sizes. It doesn't seem like, and by the way, it does seem like maybe there's that like equilibria right there, exactly where we identified it, but it seems like this is sort of spiraling out of control right here to where, notice that as these spirals continue to happen, I'm kind of expecting for them to grow to where they're like budging up against this right here. Now, what I don't really think is happening is that almost any single initial condition will lead to rabbits being nearly wiped out and then to foxes being nearly wiped out. Like, that's not really representative of what I think biological populations do. And all of this is just because we're getting bad approximations right here, bad numerical approximations. So what I'm going to do is I'm going to make this smaller. And in fact, I think I'm going to go even smaller than that. Let's do it 0.005. The other thing I want to do is I'm going to switch to a better technique. Rather than the Euler technique, oh man, that improved a lot already though. I'm going to go to the Runge-Kutta-4 method right there. And what we're seeing now is, now this graph is describing, it seems like this behavior should just straight up be cyclic, right? This is saying we're now just going to experience some natural cycle right here, where it seems like we're just going to experience that cycle, where we said, if we start out with there being a lot of rabbits, then the foxes are going to eat them, which is going to grow the fox population. But once the fox population is huge, it causes a decline in the rabbit population. Decline in rabbits causes decline in foxes. Decline in foxes causes growth in rabbits, right? And then that pattern is going to keep on going around and around and around. This seems a little bit more representative to me of what I would naturally think that this system should actually do here, which is repeat its behavior, right? If we ever got to a point where there was a very extreme discrepancy between the rabbits and foxes, like where my cursor is right now, then we should expect to see now. I'll tell you right now, when we go to build our grapher next week, or 2 weeks from now when we build our 2D grapher, this curve right here is going to do what these ones do, which is it's going to take a giant swoop around, and it's going to come back around over here. So if we do start with a tiny number of foxes and a ton of rabbits, then the rabbits are going to blow up in size. But eventually there's going to be so many rabbits that the foxes are going to eat the heck out of them. And then there's going to be a ton of foxes. If there's a ton of foxes, it's going to eat almost the entire rabbit population. And notice that curve right there I just clicked on, it almost perfectly just met up with that one over there, right? So that's the super highs and lows that we're experiencing out there. Not necessarily what we typically expect to see. So I think it's natural for us to have initial conditions that exist a little bit more right here. A bit of a cyclic up and down in their population sizes, but not anything that's causing us to get catastrophically low in our population sizes that are out there, right? The other thing that I want to look at here is the other graph I suggested to you. So I'm going to clear these. Oh, by the way, real quick, notice that if I keep on clicking in closer and closer and closer, we're getting these tighter and tighter circles. Notice where my cursor is right now, it's right where we're at the center of all that. Well, that decimal, you can see it down right there, 1.11, 1.66, that is like literally almost exactly that 10 ninths and that 5/3 right there. I am sitting on exactly the fraction. 10 ninths is 1.1 repeating, and 5/6 is 1.6 repeating. So I'm hovering over like almost the closest pixel I can get to right there to where we did find an equilibrium. And that seems to totally agree with what we found, that there is this place where the behavior is different, right? Where nothing changes. If I click there, there's not like some swoop around. It just stays there forever. It's a circle with an infinitely thin radius, or an egg shape with like no change to it, right? So that circle is just sort of sitting there. So that very much agrees with what we found algebraically right there for that equilibrium. So I want to show you now that I'm going to clear these guys and just get a couple, or just maybe like one representative graph on there, right? So that's maybe something we should expect to see, the rise and fall of the rabbit population, how they're sort of following each other in size. Well, if we scroll down a little bit, there's going to be some other graphs that we could see. Here's our numerical solution tables and time plots for systems. So what I'm seeing here is this. Fox population small, rabbit population big, fox population big, rabbit population small. It seems like they're just following what the next one is doing right there. If one gets big, that causes the other to get big. If one gets small, it causes the other to get small. They follow one after another, and it seems like they are cyclic, they are repetitive. And so I'm asking you right now, do you know any two functions that are cyclic and repetitive where one follows another? And where collectively in a two-dimensional graph, when you combine their ideas together, it makes almost circles? Well, either the answer is yes, or the answer is you forgot all the math you've ever learned in the last 3 years. And the answer is yeah. I'm kind of expecting to see something close to some sine and cosine curves right here. So check out what this graph is doing. What this graph is doing is it's giving me just a graph of my x equals solution and just a graph of my y equals solutions separately. Since this is a system of equations, or system of differential equations, there should be two equations, an x equation and a y equation, that collectively, parametrically, create this graph right here. Since this graph is basically a circle, you should be expecting the parametric equations for a circle, which is sine and cosine. These aren't exactly sine and cosine, exactly in the same way that this isn't exactly a circle right here, right? Super cool. This is also giving us information like at what time relative to this initial condition, how much time do I have to wait before x and y values are some certain thing. You can even see the change in x population, the change in y population. What's this arrow do? Show details. Ooh, they're generating all this stuff for us out here. So you should have no idea what all these K's are right now. We will generate all of those K's in 2 weeks when we go to do our programming stuff with making the Runge-Kutta method. That'll be 2 weeks from now. We'll do the simple Euler's method next week right there. I don't want that here for right now, but we will be calculating. We'll be basically building this exact table, this exact graph, and this exact graph. That 2 weeks from now, we're going to produce 100% of this all by ourselves right here. And it's going to be nice. We're going to write all the code to make all this stuff happen. Ours will be slightly less nice, but it will be ours. Yeah, so just some nice things that we can see here, that we can look times into the future and see what the nature of the relationship is between these two populations, and we can exactly see that their behavior does follow the other population's behavior, kind of exactly as we thought was going to happen. These graphs are going to be really useful for us here. So this is kind of one of those things where like this is our phase portrait, in a sense, our essential graph right here, but this is really parametrically defined by two equations, x of t and y of t, which individually are graphed right here. So this is x of t, y of t. This is the parametric graph that is x of t, comma, y of t. And you are technically choosing an initial time when you click a location that's on this graph right here, and an initial x and y, and it's plotting where they're going to go from right there. Right? Super cool stuff right here. So this graph is going to be very relevant to us from now on, so recognize that I'm going to care a lot about this one as well as about this one as we go to analyze things out here. Right? So here's our important stuff. You got to be a little bit capable of modifying these. We're going to learn exactly what these controls are exactly doing in the next 2 weeks when we write our own code. Clicking on lots of these to see what our solution curves look like, checking out our individual solutions and understand they're related to those. And by the way, you can pick any of the initial curves that you've clicked up here. All of these are, it even throws it on there right there for you. I think that black dot right there is exactly this point that's right here. And then if I pick like some other point out there, 1.1, 1.5, did it do that? 1.1, 1.5? No, did it not do that? That's weird. In any event, whatever, we can kind of, I thought that it was the case that when you click a new one up here, it does. Every time you click a new one up here, it auto-updates this to be that one right there. And then you can go back and look at the previous. So these are, okay. Tiny thing right here. I'm clicking this drop-down menu right here. You can't see it because of the way that I'm sharing my screen, but there's like a box of things that you can select, and it's all the initial points that I have clicked up here. So very cool. We got two graphs over here. So we care about this now down here too, and just recognize that it's in a drop-down thing that is below the basic graph stuff right here. Cool. So let's pop over back to Microsoft Word and carry on here. So we're talking about visualizing our systems here, and we just saw it did a pretty good job for us right here. Now, one of the things that's a little bit upsetting for us right here, and actually, sorry, one thing I want to do real quick here is, one second. Click this just so I can grab it, throw it into the notes right here. question I'm now asking is, how should we be classifying that equilibria that we saw that's sitting at that center point right there, that 10 ninths, 5/3? Notice that our only previous classifications were sink, source, and node. Uh-oh, now I'm not allowed to draw anymore, am I? I just don't understand why you hate me so much, Microsoft Word. It's just not that hard. Only equilibria classifications we've seen so far are sink, source, node. This one at 10 ninths, 5/3 doesn't seem to fit any of those descriptions. So basically, I'm just saying the answer to this question is, I don't know, but it's not any of the ones we've seen so far. That one at 10 ninths, 5/3 is not a sink. Things aren't moving in towards it. Not a node. Things aren't like moving into it from one direction and out of it from another direction. Not a source. Things aren't coming out from it. Things seem to be revolving around it. It seems like we've got some new classifications that we're going to want to consider for our equilibria, since it seems like it's possible for us to have places of no motion where the behavior near it isn't just going in or just going out. So I'm saying my answer to this is, I don't know, but it's apparently something we're going to have to think about here in the future. And I guess to get ahead of myself, what I'll say to you is, Chapter 3 is by far the biggest single chapter that we're going to cover in this class. It's going to take us a lot longer than Chapter 1, even though it's fewer sections. And Chapter 3 is going to be basically all about saying, how do we classify all the possible types of equilibria that there could ever be in a system? And it's going to turn out there's going to be kind of a lot of them, not just like two or node. There's really just two here, right? Node is sort of like a half source, half sink, right? Not quite the limited scope that we're going to see coming up here. So one thing we might want to do is update this equation, right? One thing that we know is that this 2r term is suggesting that with no foxes, the rabbit population would just grow exponentially. And we know that that's not really that appropriate, right? So we already know how to fix this, right? So it's typically the case that predator populations very rarely just get massively large, but it can be the case that prey populations get very large. So let's introduce a carrying capacity term to go along with this. So all I've done is just multiplied 2r by what we already recognize as a carrying capacity term associated with populations, right? So you're already used to that term right there. This is like our original population differential equation for including carrying capacity right there, right? So now that I've updated this, I want to go graph this over it with technology, but first I want to stop and let's see if we can graph some stuff here first. Let's draw the individual phase lines for rabbits and foxes and ask what this tells us for what to expect from the phase plane here. Right? So if we're looking here at dr dt equals 0, that's our 2r, 1 minus r over 2, minus 1.2 rf. Well, one thing I can see here is that in this case right here, it seems like there's going to be one rabbit population amount that we can have, where if r is equal to 0 and f is equal to 0, then it seems like, let me just write both these right here real quick. So the phase line for rabbits with no foxes. Right, we're doing the simplest version right here. The phase line for rabbits with no foxes. And a thing I'm remembering, by the way, is that in our 2D grapher over there, our rabbits were on the x-axis and our foxes were on the y-axis. I just named them x and y. So to that end, since I'm about to draw the phase line for rabbits, I'm going to draw the phase line horizontally instead of vertically right there, because that's about to be an axis on a graph, right? So for our rabbit phase line here, one of the things that I'm seeing is with no foxes, I'm ignoring this whole second term, right? No foxes means foxes is 0, so that term is gone. Well, you know exactly what's happening. R equal to 0 is one of our equilibrium points, and R equals 2 is also one of our equilibrium points. We know that we should be growing out of this one. That says if you're between 0 and the carrying capacity, you grow. If you're above the carrying capacity, you should decay down to it right there. Right? That's one phase line for the rabbits. Then we can do the same thing here, phase line for foxes. So this is saying to me that if we include a carrying capacity term, the rabbits should be able to reach equilibrium with their environment with no predators, because they're just going to grow to however much their environment can handle, however much food there is available, space for them to live, and they'll just settle right there. Foxes, on the other hand, depend on the existence of rabbits to exist. And so you should notice that if there's no rabbits, then the only way that the df dt is equal to 0 is if f is equal to 0. I'm going to draw this as a vertical axis because that's what I've got that graphed as my y-axis in the 2D one over there. And so that says to me at 0, this is r equals 0, this was r equals 2, this is f equals 0. And what we know is, therefore, if there's no rabbits, the fox population is going to decline the whole dang time. So what I'm expecting to see is to be able to combine these two together. Okay, is that a thing? Do I now have, I think I have audio again. It might sound slightly different. It's through my laptop now instead of through my earbuds. I believe I still have audio right here, and that you should still be able to hear me here. If anybody's watching live, you can confirm or deny that for me here. My earbuds are my microphone. It's not for hearing, it's for the good microphone. So to continue on here now, I am trying to build my phase plane, right? So I don't know how to make the whole phase plane, but I at least have this good idea now that on the axes, I know what to expect. I know to expect an equilibria here. I know to expect an equilibria here. And notice that this dot that's right there is the same as this dot that's right there. That's the 0, 0 location. Further, I know that this one right here should have arrows pointing to the right. I'm just drawing this. I'm literally just copying these together right here. I'm just mashing these two things together into one graph. So basically what I'm saying to you is we can at least figure out what the axes look like in our phase plane out here, even if we don't know how to generate like the stuff that's going on in the middle right now. We can at least form up these axes right now. So now let's go to technology, see if we get stuff that at least agrees with our partial picture right here. That hopefully we'll end up agreeing is representative of the overall picture. So all we got to do when we pop back over into the grapher is I just need to introduce the 1 minus r over 2 term in association with the rabbit population here. So let's do that. And I think I now have audio again as well right here. Okay, coming over here now, all I'm going to do right here is multiply this guy by 1 minus, and what is it, x over 2, right? Now,
It looks like this has changed our graph quite a bit right here. I hate that it keeps those curves on there. So here's what I'm thinking to myself. I'm going to graph some more of these guys. And by the way, I'm going to back off on this a bit. One of the things that I'm learning here is that this seems to do a certain number of steps. So when your step size gets small, the length of the curve that it's drawing gets shorter, even though it technically should kind of go on forever. So I'm going to at least make this 0.1 so that the curves get a little bit longer. And here's the stuff I'm seeing. So it seems like there's some other equilibria that's hanging out right here. Right? The other things that I'm seeing are, it seems like I still see this like axis location where it seems like 0, 0. Oh man, you see that orange one bust up right here? It does seem like things are growing to the right on the bottom down there. And I'm going to do a little bit of flipping back and forth, just like we had here. These arrows pointing to the right, I just saw those crop up right here. I'm also seeing when we come back over here that if I start over here to the left, I am seeing that when we're on the axis, these curves are moving directly to the left. I am also seeing things like when we start with tons of foxes and no rabbits, that the fox population will sharply decline. But I'm also seeing that there's another equilibria that we're experiencing out here, like, 1.1 and like 0.6 or something like that, which, by the way, we could algebraically go solve for this guy right here. It's at like 1.1, 0.76 or something like that. 0.75 maybe, 1.1, 0.75 seems to be an approximate location of another equilibria. But man, again, I asked the question, like, how would you classify it? It does seem like it is sort of like a sink, but it's clearly a little bit different than our traditional sink as well. It's a little bit weird. It seems sort of like a sink is, I think, how I currently want to classify that guy. So let's come back over here into Word. Let me snip this thing. Throw it into our diagram here. Cool. So it seems like it seems like I have an equilibria at 0, 0, which seems to be sort of like a, oh gosh, even that one's not obvious, right? Because it seems like some solutions are tending down towards it and others are moving away from it right there. It seems like we have an equilibria at 2, 0, 2 for the rabbits, 0 for the foxes. And it also seems like there's this one floating out here, which is at like 1.1 and like 0.75 or something like that right there. But it's sort of unclear how to classify all of these. You're going to let me do this real quick here. Oh, thank you so much. Every once in a while, Microsoft Word and I are good friends. I just got to move my point right there. Wish I would have done that a second ago. Yes, I'm drawing now. That should be an eraser. Oh, come on. Okay, I lied about the friendship thing. It hates me. I just don't know what it's doing when it does this. As soon as I can write, I'll get back to doing this. I'm not doing anything different. Oh my gosh. Okay. Here we are again. Okay. This guy seems like a sink. really know what my good word is to kind of fix the fact that like it's not just like things are just going into it. They're like swooping into it. We're going to end up finding out there in chapter 3 there are many different types of sinks, and we're going to want to decide what type of sink is that. But it is clearly the case that our trajectories are moving towards that equilibrium point that's right there. But there's a couple different ways that can happen. And that's one of the things that we're going to want to look at out there in chapter 3. Right? So now we've been looking at a bunch of this population stuff. We've seen some phase planes out there, talked a lot about rabbits and foxes. But I want to say to you, like, this isn't biology class, although that's all we've talked about today, right? If this really were a science class, this is definitely a physics class and not a biology class. And so we should get back to doing some physics. And again, I don't care if any of you guys are physics majors or not or anything like that out there. Always remember that all of calculus was invented very specifically to do physics. It's just that after the fact, we realized that all of the math that we'd sort of created to describe physics situations also applies to tons of things like biology populations and so many other things out there. But the original invention purpose, the necessity that caused us to go and create calculus was for physics. And so for at least historical purposes, it's always going to be part of this class. Even if you're a biologist taking this class, it's part of the history of differential equations and calculus in general. So we're going to learn some physics now today, and we're going to see some super cool stuff here so this is kind of our conclusion right here. It's kind of changing gears and looking at a second example. We'll spend less time on it. But very, very cool way to tie this up here. So now for something completely different. This certainly isn't biology class, but it's a physics class. And an example is, let's talk about the position of a mass on a spring. My general diagram for this guy is going to be, there's like a wall and the ground. We're going to mount the spring to the wall right here. And there's going to be a block on the end of it, right? It's going to be attached to some mass that's sitting right here. Now this position right here, that's what we're going to call x equals 0. That's its natural rest state. And so you could imagine that we're going to do things like grab that mass on the spring and pull it out to a positive x value. If we were to release it, then it should do a bunch of sliding back and forth. Similarly, I could push the spring in, compress the spring so that it's at an x location of like -2. And then if I pushed it in and let go, then it should push out and then do a bunch of back and forth action right there. What I want to do is say, given an initial location, like x equals 2 if I pull it out, or x equals -2 if I've compressed it in, and then I release, or even better yet, if I pull it out and then like throw it back in towards itself, can we describe what the position of the spring will be over time? That's kind of going to be our goal right here, right? So, in 1678, there was an English physicist named Robert Hooke, and he published a paper describing what we now refer to as Hooke's law. Hooke's law says the force that is applied to a spring is proportional to the displacement of a spring, right? So the spring force, either the pulling back or the pushing out, is going to be proportional to how far away the object is from its natural rest state, x equals 0 right there. So this equation is going to look like the force is constant of proportionality, proportional to the position. I left a little gap in there, and you can maybe read the sentence that's at the bottom of the screen right now. One of the things that you should notice is that if I pull the spring out, pull the mass out so that it's at a positive x value, right? We've gone to the right at x equals 2. Then the force that the spring is pulling on is to the left, even though the x value is to the right. Conversely, if I compress the spring so we're at x equals -2, then the force is the opposite direction of that. The force is to the right when our position is to the left. And so therefore, we want to introduce that negative sign right there that says the force is in the opposite direction of the location. If the location is to the right, the force is back to the left, because it's always moving back towards the center. Right? If you're to the right, you need to move to the left to get back to rest. If you're to the left, you need to move to the right to get to the rest. That negative says we are, and that's exactly what my next question is here. In this equation, how do we interpret the negative sign? And this is going to say to us, spring force opposes position. Now, I'm writing some extra stuff alluding towards some things later. there are other forces that may oppose or support position, or maybe things other than position. In a week or two, we're going to be writing some sentences that look very, very similar to this, but we're going to be describing things other than a spring force. But I'm going to write a similar sentence with similar interpretations of the words that are in there. Right? So this is going to describe our spring force, but this doesn't really help me figure out if I want to solve this for X, I'm going to need to know things like what's the force and stuff like that. So how do we describe force? Well, a few years later, in 1687, there was some bro, Isaac Newton, looked it up, another English physicist. He published a paper that included Newton's laws of motion. There's 3 of them in here. I know that all of us are vaguely familiar with all of these. We want to identify which one we care about the most in this situation. His first law of motion says, and I know everybody's heard this phrase, an object at rest will remain at rest. An object in motion will remain in motion unless acted upon by an external force. If the net force acting on an object is 0, then the velocity is constant. That's what it's saying. And this is what we typically use our layman's terms to describe as inertia. Please never say the word inertia to your physics professor. Don't do that. Newton's law number 2. The rate of change of momentum over time is proportional to the force applied. That seems to be describing how forces work here. So that might be what we want to help relate our Hooke's law to being actually able to find what that X expression is going to be. That's the thing that we're going to care about here today. Newton's third law is the one that says that all forces between 2 objects are equal in magnitude and opposite in direction. So that's saying things like, you got to understand that when you are pushing really hard on a wall, the wall is pushing back on you exactly equally as hard. The magnitude of the forces are exactly the same. The direction of the forces, you're pushing on the wall is pushing back on you with an exact equal amount of force because there's no motion. So there has to be 2 equal but opposite forces that are adding together to make the 0 motion that's occurring right there. So all forces between 2 objects are equal in magnitude and opposite in direction. And this is kind of a slightly unintuitive thing, right? When you press down on the desk, you don't feel like the desk is pushing up on you, but it has to be. Otherwise, the desk would be going down in position and it's not staying right there. So there has to be an equal but opposite force counteracting your downward force to result in there being no motion right there. Right? But again, we care in our case right here about this second law. So let's use this. Notice that Newton's second law is actually about momentum. And I know that a lot of people are comfortable with the acceleration phrasing of this one, but Newton's second law is actually about momentum. So let's go ahead and kind of fix that right here. Basically what law number 2 says is the rate of change of momentum over time, rate of change over time of momentum, which is typically given by P or rho, is proportional to the force applied. All right, so there should be some proportionality relative to the force right there or something like that. Well, what is the rate of change of momentum? Well, momentum is mass times velocity. If we assume that mass is constant, then this is really mass times the derivative with respect to time of velocity. And we know what the derivative of velocity is. This looks like mass times acceleration. Force equals mass times acceleration, right? I'm going to lump the K in with mass over here right now. And that's going to be force equals mass times acceleration. I'm not going to mention that right there. The whole point here is Newton's second law is actually not a statement about acceleration, but about momentum. And so as long as the mass is constant, which is a very reasonable assumption for us to make in like most all physics scenarios right here, then we just get force equals mass times acceleration, right? We're proportional to that thing right there. And the mass is our constant of proportionality in this case right here. So now we have 2 equations from Newton and Hooke that together are going to help us decide where this mass on a spring is going to be anytime in the future. Force equals mass times acceleration, and force equals negative K times the position right there. And so I'm just going to set these equal to each other and say mass times acceleration equals negative Kx. But then you should be saying to yourself, Tony, isn't this calculus class? And I'm saying, yeah, man, of course this is calculus class. Acceleration is the second derivative of position. And so I'm going to just move my terms over to the other side and say mx double prime plus kx equals 0. seems to be a second order differential equation that's describing the position x at any time t. That's an x of t function that we're looking at right there. And I'm using my, acceleration. All right, we know that velocity is our x single prime. Our first derivative of position is velocity. Second derivative of position is acceleration. X is just straight up position. So we get that that x term that's going to be sitting right there. Right? And further, I feel like people typically don't like to have coefficients on their highest order derivative right there. So it's pretty typical to divide that out and say plus k over m x equals 0. And so this guy right here is our simple undamped harmonic oscillator. So let's talk about these words right here. It's a simple oscillator because there's only one spring that's affecting this. If you're thinking about like a double pendulum or something, that's no longer a simple system right there. Undamped is a really important word because we're going to change this word soon. Undamped, a damping force is a force that causes things to like decay over time in motion right here. You should think specifically in our case right now, you should be thinking about friction, right? I'm saying that this is undamped, meaning this is on a frictionless surface right here, according to our very simplified assumptions. And so if I pull this thing off and release it, because there's no friction, it should just go back and forth forever because there is no damping force that we're currently including in this. What you know is that what friction should do is cause this thing to like decay in its amplitude over time until it just comes to rest back at its natural rest state. Once we introduce that damping term, we're going to end up seeing our solutions are going to behave exactly like that, right? So my question to you is, since there is no damping, if we were able to solve this second order differential equation, which we certainly don't have any techniques for solving these guys necessarily yet, if we were able to integrate with respect to t twice and actually figure out how that's going to work, what would our graph look like? I mean, what should x of t be doing? And the thing that I'm noticing here is that we're starting at, so this is our time, and this is our position over time. So this is me saying something like we're starting by pulling the spring 2 units to the right. But remember, we're not in a true system right here. We're saying there's no damping force. That's sort of our imaginary part of this system right here. So imagine that this is on like the slipperiest ice known to man, right? When I release this thing, it should just kind of go back and forth forever. So we're going to go from 2 to 0 to -2 to 0 to 2 to 0 to -2. Oh, do you know any equations in math that do that? I think so. And remember, there's no decay in amplitude because there's no damping. Yet. However, if there were a damping term, I would expect a very similar type of behavior. I would just expect to see the amplitude of my sine or cosine curve get smaller over time, kind of honing in on 0 right there. You should think to yourself, do you know any equations that do that? Because we should be getting them out of our solutions here coming up in a couple weeks. Man, I wish I could solve this equation, you know? I wish I could solve this equation right here for x. It would be super cool if we could. If only there was some way that position and acceleration were related, maybe we could come up with some equation. Do you know something that relates position and acceleration? I think I do. We're working with this equation here. I know that position is x, velocity is x prime, and acceleration is x double prime. It seems to me like velocity is the thing that relates position and acceleration. So here's the thing that I want to do. Let's create a new variable, v, or rather I should say dx dt is v, right? That's easy. The derivative of position is velocity. But you should then notice that then we get that the derivative of velocity with respect to time, well, that's what we call acceleration. Well, that is x double prime. That seems to be exactly what we have right here. What is x double prime? Well, it's negative k over m x. It seems like we can convert the information from our second order differential equation right here, second order differential equation. I can make a substitution that converted this into a system of first order differential equations. This is encapsulating all of the information of our second order by introducing a new variable, v, which isn't hard for us to understand at all, velocity. And it gives us only two first order differential equations rather than one second order differential equation that we don't know what to do with. That's pretty damn cool right here. So now we want to help ourselves, because I'm telling you, I straight up want us to solve this differential equation today. And not only do we not know how to solve second order systems, second order equations, we also don't know how to solve systems. And I don't care. I think we're going to do it anyway. To make this a little easier for ourselves, let's pick one nice number for ourselves. Let's let k be equal to m so that that fraction just becomes 1 right there. And let's go ahead and see if we can think about what should be happening in this system. So my system now looks like dx dt equals v, and dv dt equals negative x, right? K over m is just 1 because I picked the nicest possible values for my parameters here. So, and now I'm going to give you even an initial condition. Not only are we not solving this generally, I'm saying I want to know a particular solution here given an initial condition. The initial condition is that we're going to pull the mass in the spring 1 unit to the right, and then we're going to release. What I want to know, with this being your very first day of systems of differential equations, is straight up what's the solution to this system? And I want you to answer by just looking at this thing, because you know calculus. My question to you is, we want to find functions x and v, both of t, where the derivative of x gives you v, and then you take the derivative of v and it gives you negative x. Do you know an equation x and v that satisfy that? Where you take the derivative of one and it gives you the other, and then you take the derivative of the other and it gives you back the first but times the negative? Yes, you do know these things because you know trig. And you better be thinking trig stuff because that's what we're thinking about for our solution here for x and t, right? It seems like x and v should be some combination of sine and cosine. My question to you is, what combo works for our initial condition? So what is our initial condition here? It seems to me like my initial position, initial velocity, what are they? Well, my initial conditions, we pulled the mass 1 unit to the right, so my initial position is 1. And what is the initial velocity of the mass in the spring? I'm just going to let go. So at the instant I let go, it had no velocity, right? So there should be a 0 for the velocity term right here. Otherwise, you could think of the fact that maybe I would like pull it to the right and then like throw it to the left or something, in which case it would have an initial negative velocity, or that I'm like kind of like pulling it and releasing as I do the pull to where it has an initial position right at the release, but it has like a velocity because I'm still like doing it partway through. That would have an initial positive velocity right there. I'm saying I'm just pulling it up to rest right here at one unit further to the right and then releasing. And so at the instant of my release, it for one instant has 0 velocity, but then is going to certainly have a negative velocity as it moves to the left. So what I'm trying to do is come up with x of t and v of t that are some sine and cosine, and I want it to be the case that position starts at 1, velocity starts at 0, and as time gets slightly larger, our x should get smaller, and our v should also get smaller, right? Because we should have a negative velocity and we should be losing position right there. So we're trying to decide what are some sines and cosines that we could be using to kind of help come up with this. I'm noticing that if I pick like x equals sine of t and v equals cosine of t, That would technically agree with this, but it wouldn't agree with our initial conditions, because if I plug in 0 for sine, I get 0 instead of 1. If I plug in 0 for cosine, I get 1. So it doesn't seem like that's going to be the case right there. Also, so this disagrees with initial conditions. On the other hand, I could maybe then pick, okay, I could say, okay, x is cosine and v is sine. Does this agree with our initial conditions? If you plug in 0 here, you get 1. If you plug in 0 here, you get 0. So that agrees with our initial conditions. But no, now I'm asking, is the derivative of xv? No. The derivative of cosine is not positive sine. It's negative sine right there. So that also doesn't quite seem like it's going to work. So maybe instead, so I'm going to say no, disagrees with diffie q. So maybe instead we do x equals cosine of t and v equals negative sine of t. Now I'm noticing the derivative of x, the derivative of cosine is negative sine, so that's good. The derivative of negative sine is negative cosine, so that works. If you plug in 0 for t, we get 1. For x, and if you plug in 0 for t, we get 0 for v. So this seems to be my solution to the system of differential equations, which was actually a rewritten version of a second-order differential equation. How cool is that? So we're actually kind of coming at some solutions right here by visual inspection, because we know how to kind of interpret periodicity, right? What will this look like in the phase plane? My answer to you is you already know, because you know about parametric equations, right? So if I go to the phase plane, if I try and graph this thing in the phase plane, x of t and v of t, what you know is that this is going to generate the unit circle. It's a parameterization of sine and cosine. The only thing that's not directly obvious to me right now is what direction is it going. But we can recognize that this is our initial condition right there. That's our ICs right there. And I want to know, what are the arrows that I draw on this? Every parametric curve gets arrows, and so does ours, because our position and velocity, like, it matters what direction you think we're traversing here. If we went this direction, then this would be saying our velocity is positive at first. If we go in this direction, it says that our velocity is going to be negative first right here. I'm thinking that because I'm pulling this mass on the spring and releasing it, its velocity is first to the left in a negative direction. So I am quite convinced that this guy should be going in this direction as it rotates around. So I'm going to go graph this guy now over in our graphical phase plane plotter, and I am expecting to see perfect circles, and I'm expecting to see them rotating clockwise here. So let's pop over and see if that's exactly what we get. Remember, our equation that we're going over to graph is dx dt equals y, and dy dt equals negative x. So dx dt equals y, dy dt equals negative x. Oh man, I feel like I see some circle looking stuff. Notice real quick right here, this is not a square box, and so I'm not going to get square pictures. You should also notice that it typically gave this x range as 4s instead of 3s. I do think that this is like a 3x4 proportion box right here. So I'm going to go -3 to 3. The x should be more, -4 to 4. And then down here, -3 to 3. Awesome. Way too many curves on here. But we can go ahead and give ourselves the exact initial condition that we had. Here is, if you're looking at my decimals that are showing up right down here, the decimals show up right here. If I go over here, I can see that I'm about at, this is, approximately my 1, 0 right there. And what do you know? We're getting a circle. It's a perfectly circular shape, and it is rotating in the clockwise direction exactly as we predicted that it was going to do. Very cool here, right? Throw a couple more of those on there because I want to throw this into our document here. Perfect agreement with our, and so I don't know, did you expect that we were going to be solving systems of differential equations and producing their graphs today all by hand without actually knowing anything about their solving techniques? I'm expecting that the answer to that question is no. Pretty cool stuff. Oh my gosh, Microsoft Word's killing me. You know where I want it. Yeah, there we go. All right, tiny graph, that's okay. Yeah, I hate that it doesn't want me to put this below the, whatever. It's okay. Here we go. We got our graph in there. So, okay, whatever. I guess I put that in here for a reason. There's all the space I wanted. Finally, what do the graphs of these individual solutions look like for x of t and v of t? Well, we know that exactly. We're just graphing cosine and negative sine right here from the initial conditions of 1, 0, right? So, and I'm just going to say it right now. We saw the rabbit and fox populations were doing this basically a sine and a cosine because it was one trig function following another. It's exactly what we're going to see right here, right? So what I'm going to say to myself is on my axis right here, here's my time axis. Now, here's the thing I'm going to do that's important for the drawing. Remember, we're putting two graphs on here. So we're going to get both. I should immediately get rid of that guy right there. We're going to get both I'll draw it in blue here, x of t. So what's the x of t graph look like? X of t is cosine. And x started out at 1, and that's good because that's what cosine does. So x started out at 1, and it's just the cosine function. Our other graph that we have available to us right here is our v of t graph, which is also going to be plotted on the vertical axis right here. We know that v of t started at 0. That was our initial condition for v of z, or v of t. V of t started at 0, and we know it's the negative sign. Oh my gosh, I've been in the wrong thing this whole time. I'm sorry, everybody. Coming back over here. Our graph that I'm trying to draw right now is our individual solution curves over here for these two guys. So we're recognizing that the x of t graph, all right, I'm gonna back up so we've actually got our information right here. We've got x of t, v of t. This was our cosine graph. This was our sine graph. The ICs were x of 0, v of 0 equals 1, or sorry, 0, 1, right? No, 1, 1, 0. Blip, blip, blip. You should notice then that my x graph, the cosine graph, did indeed start at a height of 1. My sine graph, the v graph, did indeed start at 0 right here. And now I can go ahead and draw my negative sine graph. Reaching the minimum right there, crossing right there, reaching the maximum there. So it should be looking pretty much just like this right here, right? And what I'm now going to go do is ask the digital grapher to do it for us. And we're going to look over here and just come down here and just open this thing. And say, oh, what do you know? This is exactly the graph that I just drew. The only difference is this one, I clicked on a couple other ones right here. So let me clear the curves. And again, if we start right here at essentially 1, 0, then when I come down here, here it is exactly. The height is 1 for the x to start. The height is 0 for the y or the v to start right there. So notice I'm plotting the initial conditions there on the y-axis. Initial condition of 1 for x, initial condition of 0 for y, and then they're following the trends associated with the sine and the cosine graphs. And the thing that should be somewhat blowing your mind right now is that these graphs are the same graphs as we saw from the rabbit and fox populations, essentially. Those weren't perfect circles. They were slightly egg-shaped. But isn't this kind of crazy that we're seeing that the graphs associated with position and velocity of a mass on a spring are almost identical to the relationships between rabbit and fox populations over time? That's pretty cool and kind of helping us see that, yeah, this is math that's tying together physics, chemistry, biology, all the sciences out there. Hopefully you feel extra good about this being like our common language of discussion, since we're seeing solutions for biology problems are nearly identical to our solutions to physics problems out there, which is super cool. So one of the things we're going to talk about in our next video here is we're going to talk about the geometry of systems of differential equations. And so the question we're going to start asking is, where do these graphs come from? How are they producing this plane with all these arrows that are in it out here? Where are we getting these things from? And we're tending towards, how do we produce the, like literally, like what's the code we're going to write to produce this? What's the algorithms that are associated with creating these graphs? So think about the geometry of these systems a little bit more. The graphical perspective is what we're going to hit in tomorrow's video in 2.2 right here. So that wraps it up for us today. I hope you enjoyed both doing some good biology and some good physics here today. Yeah, I'll see you guys for some geometry of systems in 2.2 tomorrow. Have a good one, everybody.